Now, we will take this equation again, we will solve it. We will be getting here x naught to x is equal to u t minus this t and 0 to t plus a t square by 2 0 to t. Now, here we can write x minus x naught is equal to u into t minus 0 plus a into t square by 2 minus 0. So, this we can write as a displacement S. So, we can write S is equal to ut plus half at square. So, this is the relation between displacement and time, but when acceleration is uniform. So, now we can go for the third relation also. Similarly, that is a velocity displacement relation. So, see here in velocity displacement relation by calculus method, here let us first write this is here velocity displacement relation. Here we can write first A is equal to dv upon dt. This is instantaneous acceleration, but you know we need to find out displacement here. So, obviously, A should be in terms of displacement. So, we can also write here dv upon dx into dx upon dt. Now, this dx upon dt is velocity, instantaneous velocity. So, we can write A v into dv upon dx, and then A dx is equal to v dv. Now, we integrate it again by the taking the limits. A dx x naught to x is equal to v dv, that is u to v. Initial position, final position, initial velocity, final velocity. As we know A is uniform, so we can write it here A x naught to x is equal to v square by 2 u to v, or we can write A x minus x naught is equal to v square by 2 minus u square by 2. This we can replace by s. So, we will be writing 2as is equal to v square minus u square, or we can take v square is equal to u square plus 2as. So, this relation is here velocity and displacement relation. So, now we have seen all the three relations by using calculus method. So, we have done by both the methods. So, one is by graphical, another is by calculus method.